There's an underwater wall of oysters that's working to filter and clean the water. These are called vertical oyster gardens.
500,000 tons. Let that number sit for a second. Not concrete, not engineered reef modules, not some cutting-edge composite material dreamed up in a research lab. Oyster shells. The same shells scraped off dinner plates in Florida's seafood restaurants and swept off processing plant floors, loaded onto barges, tipped into the Gulf of Mexico. And the people who did it weren't even sure it would work. This is the story of one of the most controversial, most mocked, and ultimately most consequential ecological experiments ever run on American coastlines. A story about how something critics called reckless ocean dumping quietly became a blueprint for saving coastlines around the world. A story about bacteria, hurricanes, fish that weren't supposed to be there, and a charter captain who spent years fighting a program he would eventually call the best thing that ever happened to his fishing grounds. But here's what makes this genuinely extraordinary. It's not just about oysters. It's about a question scientists are still wrestling with today. Can we actually reverse decades of ocean destruction, not in generations, but in years? And if so, why aren't we doing it everywhere? By the end of this, you'll have a completely different understanding of what the ocean floor is capable of, and what happens when humans stop fighting nature and start working with it instead. Let's start in the worst possible place. A dead ocean floor. The problem nobody wanted to talk about. Florida's Gulf Coast used to be something else entirely. Centuries ago, the shallow coastal waters near Cedar Key, near Charlotte Harbor, near the 10,000 Islands, were alive in ways that are almost impossible to visualize today. Oyster reefs stretched for hundreds of square miles. Not thin scattered beds, but dense, architecturally complex structures built from generations of calcium carbonate stacked on top of each other. Massive, filtering, wave-dampening biological machines running on sunlight and seawater. These reefs weren't just beautiful, they were functional. A single adult oyster filters between 30 and 50 gallons of water every single day. Scale that across a reef system spanning hundreds of miles, and you're talking about a water purification operation that no human engineering has ever matched. Nitrogen, phosphorus, agricultural runoff, suspended sediment, harmful bacteria, all of it drawn in, processed, and neutralized. For free, continuously, for centuries. And then in a few generations of industrial fishing, coastal development, and chronic pollution, it was almost entirely gone. By the early 2000s, Florida had lost an estimated 85% of its historic oyster reef habitat. What remained was fragmented, ecologically disconnected, and struggling under nutrient-laden runoff that fed harmful algal blooms responsible for mass fish kills up and down the coast. Water that had once been clear enough to see the seafloor at 10 feet of depth had become murky, oxygen depleted, and increasingly hostile to marine life. Here's what makes this so complicated. Once a reef system collapses past a certain threshold, it cannot rebuild itself. Not because oysters stop reproducing. The larvae, called spat, are still out there drifting in the current every spawning season, searching for a surface to settle on. But the surface isn't there. The shells of previous generations have been buried, harvested, or dissolved. Soft, sandy seabeds offer nothing. Spat that lands on sand dies. Without settlement, there are no new oysters. Without new oysters, there's no new shell. Without shell, there's no substrate. The cycle breaks completely, and the Gulf has no way to restart it alone. That was the ecological trap Florida's coast was locked in. And a small, underfunded program at the Florida Fish and Wildlife Conservation Commission had an idea that was either going to look visionary or absolutely ridiculous. The idea that made everyone nervous. The premise was so simple it was almost offensive. Oyster spat needs hard surfaces. Florida's coast is covered in soft sand. Oyster shells are hard surfaces. Restaurants and seafood processing plants across Florida throw away thousands of tons of shells every year, most of which end up in landfills. What if those shells went back into the Gulf instead? Between 2007 and 2024, the Florida Fish and Wildlife Conservation Commission ran exactly that experiment. They collected discarded shells from restaurants and processing plants, trucked them to the coast, loaded them onto barges, and deposited them onto the Gulf floor near Cedar Key in targeted locations chosen based on current patterns, water depth, and proximity to existing oyster populations. Over the life of the program, more than 500,000 tons of shell went into the water. The opposition was immediate, loud, and came from people who weren't wrong to be skeptical. Environmental groups raised real concerns. Dumping 500,000 tons of anything onto a seafloor is not a neutral act. What would happen to soft-bottom communities already living there? What about sediment disruption? Altered current patterns? Were they trading one ecological problem for another? Local fishermen were furious. Charter Captain Mike Lenz was one of the loudest voices against it. He testified against the program, showed up to public meetings, and warned in plain language that this would destroy what little his family had left after generations working those waters. Even the scientists running the program were uncertain. The theory was sound, but the Gulf has a long history of humbling people who thought they understood it. The commission made a calculated decision. These shells were going to landfills anyway. If there was any reasonable chance they could function as reef substrate and restart the biological cycle, the experiment was worth running. They pressed forward. What happened next is the part nobody had fully prepared for. 18 months later. When the first monitoring teams returned to the deposition sites 18 months after the initial shell drops, they were braced for the worst. Sediment burial, smothered seabeds, maybe a few scattered barnacles suggesting minimal colonization. Dr. Krimsky, a shellfish habitat specialist with the Florida Fish and Wildlife Conservation Commission, stopped mid-sentence during the team debrief when the water sample and sediment core results came in. Life was colonizing the shell mounds. Not in 2 or 3 years, the standard minimum timeline for any artificial reef project to show meaningful biological response. In months. Clusters of marine organisms forming at rates with no precedent in the scientific literature. The shells weren't sitting as passive debris waiting to eventually be colonized. They were functioning almost immediately as biological triggers. The question was why? And to answer that, you have to go microscopic, the invisible phase. The pioneers weren't fish. They weren't even oysters. They were bacteria. And what they did in the first weeks after the shells hit the seafloor set the conditions for everything that followed. Within days, microscopic bacteria began colonizing the calcium carbonate surfaces, forming biofilms, structured living carpets that transform dead, inert material into functional microhabitat. And the shells themselves were actively helping. Oyster shells are composed primarily of aragonite, a form of calcium carbonate that dissolves slowly in seawater. As those shells released calcium ions, they created tiny alkaline microzones, localized chemical environments measurably different from the surrounding Gulf. Those chemical shifts were precisely what calcifying organisms needed. Barnacles, tube worms, juvenile oysters, all of them require specific chemical conditions to attach and begin growing. The shells weren't just providing a surface, they were manufacturing the conditions for their own colonization. Think about that. Discarded restaurant waste, actively engineering the chemical environment around itself to attract and support life. No human input, no monitoring, no maintenance, just chemistry doing what it's always done. Weeks after bacteria established their biofilms, diatoms and microalgae moved in, creating the base of a rudimentary food web. Microscopic crustaceans and larval mollusks followed, grazing on the algae. Those grazers drew the first juvenile fish. Each stage fed the next, a self-reinforcing loop building itself invisibly from discarded seafood scraps. By the end of the first 6 months, to a casual observer, the water still looked murky and the bottom still looked like sand. But the water samples and sediment cores told a completely different story. In less time than traditional artificial reefs typically show any biological response, the shell deposits had established a complete microscopic ecosystem. Sandy seabeds cannot do this. Sand offers no attachment surface, no chemical microzones, no structural complexity. The shells bypassed that trap entirely by doing something sand can never do, creating the conditions for life to build upon itself. The invisible phase was the hidden scaffolding. Without bacteria, without the aragonite chemistry, without biofilm feeding the first grazers, there is no reef, just calcium scattered on sand. The scaffolding was in place. And what came next would change the conversation entirely. The return of the reef builders. Oyster spat drift on Gulf currents during spawning season. In a healthy reef system, they find accumulated shells of previous generations, settle, and grow. In a collapsed system, they drift until they die because the substrate they need no longer exists. The deposited shells solved this bottleneck with startling speed. Each pile was a concentrated landing zone, positioned in the path of Gulf currents that carried drifting spat. The positioning wasn't accidental. The Commission had done their homework on current patterns, and it paid off immediately. Within the first year, University of Florida Marine Lab researcher Dr. Bill Pine documented juvenile oysters attaching to the shells in numbers that significantly exceeded projections. By year 2, those juveniles were reproductive adults producing larvae of their own, which settled on existing structure and added a second generation. Human hands had created the initial conditions. Nature had taken over completely. By year 3, monitoring surveys recorded an average of 847 oysters per cubic meter of deposited shells. Nearby soft bottom areas with no substrate supported virtually none, and the reefs weren't staying within the original deposition footprint. Oysters were dying, contributing shell and providing substrate for the next wave. Vertical growth, horizontal expansion. The reef was building itself outward, without any additional human input on pure biological momentum. Then came the reversal nobody expected. Charter Captain Mike Lenz had been one of the loudest voices against the program. He'd testified against it. He'd warned publicly that it would ruin the fishing grounds his family had worked for 3 generations. In 2013, standing at the rail of his boat over one of the established reef sites, he watched a school of redfish holding in the current around a shell mound. And he said something he had never planned to say. "I was wrong. I've never seen fish stack up like that in 25 years on this water." That reversal wasn't just one man changing his mind, it was the moment scientific data and the lived reality of working fishermen finally pointed in the same direction. When the fish arrived, everything changed. Reef fish don't wait for a formal announcement. The moment structural complexity appears on a featureless seafloor, they find it. And what happened near Cedar Key in the years after the reefs established themselves is the kind of data that makes researchers recheck their methodology because the numbers seem too good. Biomass around the reef sites had increased by more than 340% compared to control areas. Species diversity was up 280%. Redfish arrived first. Sheepshead followed, thriving on the invertebrate communities coating the hard surfaces. Flounder worked the edges. Snook appeared in numbers that hadn't been recorded in those waters in years. But the distinction that matters most is one Dr. Pine's team was careful to establish. These weren't fish aggregating from other nearby areas. Artificial reefs made of concrete or sunken ships are notorious for concentrating fish that already exist in a region, redistributing a fixed population around a new landmark. That looks dramatic in a survey without representing any actual increase in marine life. The Cedar Key reefs were doing something different. Juvenile fish counts, animals born in those waters and surviving to maturity there, were the primary driver of the increase. The reefs were producing fish, not concentrating them, creating conditions for survival, reproduction, and population growth that hadn't existed before. That distinction changed how Florida's fisheries managers thought about the entire program. Octopuses established territories in the reef's complex gaps. Sea turtles reappeared, foraging on invertebrate communities built up across the hard surfaces. Dolphins were observed hunting systematically at the reef edges with coordinated behavior that behavioral researchers found worth documenting separately. Every new arrival reinforced the food web beneath it, making the entire system more complex, more stable, and more resilient. Charter operators across Cedar Key began formally requesting new reef sites near their most productive fishing grounds, from the same commission they'd fought against 6 years earlier. Hotels, bait shops, and waterfront restaurants all reported measurable revenue increases tied directly to the surge in marine activity. The ecosystem was rebuilding, the economy was responding, and something else was happening to the water itself. The billion-gallon cleaning machines. One adult oyster filters between 30 and 50 gallons of seawater every single day. Run that number across hundreds of thousands of oysters thriving across the restored reef sites. Entire reef systems were processing billions of gallons of Gulf water daily, extracting suspended particles, excess nutrients, harmful bacteria, and agricultural runoff with no machinery, no electricity, and no maintenance cost whatsoever. Nature had built an industrial-scale water treatment facility out of discarded restaurant waste. The Gulf Coast has a chronic runoff problem. Nitrogen and phosphorus from farms and urban development pour into coastal waters continuously, fueling harmful algal blooms that cloud the water, suffocate marine life, and trigger mass fish kills. For decades, those blooms had been something coastal managers talked about managing rather than solving, because solving it seemed impossibly expensive. The oyster reefs were attacking it at the source. Water clarity around the reef sites improved measurably within a few years. Dissolved oxygen levels rose, nutrient concentrations dropped, and critically, those improvements weren't staying localized, they were radiating outward in a growing radius around each deposition site. Here's where it gets fascinating. Seagrass, critical habitat for juvenile fish, manatees, and sea turtles, requires sunlight to survive. Murky water blocks the light. No light, no seagrass. No seagrass, no habitat for the species that depend on it. As the oyster reefs cleared the water column, seagrass beds began expanding into zones that had been too turbid for years. And then seagrass did what seagrass does. It stabilized sediment, which reduced turbidity further, which enabled more seagrass growth. A second self-reinforcing loop triggered by the first, radiating benefits across the entire coastal system in ways the original program never anticipated. Researchers estimated the filtration value generated by those 500,000 tons of shells would have required extraordinary mechanical infrastructure to replicate. Nature was delivering it for free and getting better every year as the reefs grew larger. The results didn't stay in Florida. By 2015, Alabama had launched its own shell recycling program. Mississippi followed. Louisiana initiated massive reef-building initiatives. The Billion Oyster Project in New York Harbor adopted the same principle in one of the most polluted urban waterways in North America, demonstrating this wasn't a Gulf Coast phenomenon. It was a scalable approach to restoration. Circular environmental design, materials once considered waste, repurposed as functional ecological infrastructure, not a stopgap. A genuine long-term strategy for restoring coastlines that human activity had spent generations destroying. Then Hurricane Irma showed up to test everything. The hurricane test nobody designed. September 2017, Hurricane Irma. Category 4. Wind speeds exceeding 150 miles per hour. Storm surge powerful enough to reshape shorelines overnight. When damage assessors moved through the area after Irma passed, what they found stopped the conversation cold. Shorelines backed by the restored oyster reefs had experienced dramatically less erosion than unprotected stretches nearby, 30 to 40% less on average. The difference was visible from a boat without instruments. The stretches behind the reefs were intact. The unprotected sections had been reshaped. The reefs had acted as natural wave attenuators. Their dense, irregular, three-dimensional structure, layers of living oysters stacked on layers of shell, absorbed and dissipated wave energy before it reached shore at full force. Waves don't run cleanly along an oyster reef the way they run along a smooth seawall. They hit irregular surface after irregular surface, losing momentum, losing height, losing the energy that would otherwise tear a beach apart. Engineers estimated the reefs prevented approximately $3 million in coastal property damage during Irma alone. The total cost of the entire 17-year restoration program? Approximately $5 million. The reefs had nearly paid for themselves in a single storm event, but here's what seawalls cannot do, and the thing that makes this finding critical for how we think about coastal infrastructure going forward. Seawalls crack, riprap shifts, steel corrodes, concrete fails, always eventually. Every hard engineering solution degrades and requires ongoing maintenance to remain functional. Oyster reefs do the opposite. Storm damage triggers new larval settlement. Each subsequent generation adds height and structural complexity. The barrier grows stronger after every storm, not weaker, self-repairing in a way no engineered structure can achieve. Coastal engineers who had spent careers dismissing oyster restoration as fringe conservation suddenly had no convincing argument against it. Traditional shoreline armoring runs hundreds of thousands to millions of dollars per mile to install, plus maintenance that never stops. The Cedar Key program had achieved comparable, often superior, erosion protection at a fraction of that cost, improving every year with zero additional investment. The living structures that refuse to stay still. By the early 2020s, the Florida reefs had done something no artificial reef in the region had previously managed. They had grown substantially beyond their original footprint, the oldest sites roughly doubling in total area without any additional human input of any kind. Each generation of oysters settled on existing structure, matured, died, and contributed shell for the next wave of larvae. Vertical accumulation, horizontal spread, the reef engineering its own expansion, generation by generation, on pure biological momentum. The structural complexity had also increased dramatically. Early deposits were irregular mounds of loose calcium. The living reefs that emerged were architecturally elaborate. Vertical profiles, gaps between dense oyster clusters, overhangs, interlocking surfaces creating dozens of distinct microhabitats within a single structure. Crabs, octopuses, sea stars, and juvenile fish were all exploiting different features simultaneously, not sharing a single substrate but occupying a multidimensional ecosystem with the vertical and horizontal variation of a small coral reef. And then researchers found something that pushed the entire program into a conversation nobody had anticipated. Dense oyster reefs sequester organic carbon in their shells and surrounding sediments, trapping greenhouse gases that would otherwise contribute to ocean acidification and atmospheric warming. Oyster restoration had begun appearing in climate adaptation strategies, not just as habitat recovery or coastal defense, but as a carbon management tool. The ecological case had expanded into a climate case almost by accident, driven by data nobody had designed the program to collect. Biodiversity metrics at the mature sites were approaching levels recorded at pristine natural limestone reefs. The Gulf was rebuilding itself. The biological richness of these sites could no longer be dismissed as preliminary or fragile. The reefs weren't aggregating existing life. They were generating new life continuously, season after season, without any help. What this changes. The long-term trajectory of the Cedar Key reefs points toward something restoration scientists rarely claim with confidence, but the data suggests a self-sustaining system that no longer requires human management. The shell deposits of 2007 seeded a cycle, now perpetuating itself indefinitely. Each oyster that lives and dies contributes substrate for the next generation. Each generation expands the reef's footprint. Each expansion creates new habitat, filters more water, protects more shoreline, and supports more species. The human intervention ended years ago. The ecosystem has not. That outcome was unimaginable in 2007. It was measurable, documented fact by the early 2020s. International interest has followed. Coastal engineers in Canada, Australia, and across Europe have been studying the program specifically because it demonstrates something hard engineering approaches have consistently failed to achieve. Not just structural intervention, but biological restart. Traditional artificial reefs share a consistent failure mode. They concentrate fish that already exist nearby without generating new biological production. Fish aggregate around the new structure. Surveys look good, but remove the structure and fish disperse because the system never actually restarted. It just rearranged. Oyster shell reefs work differently. They don't just provide structure, they create the conditions for ecosystems to rebuild themselves. The chemistry changes, the microbiology activates, the food web assembles from the bottom up, and once underway, it becomes self-sustaining in a way engineered structures never achieve. That is the lesson of 500,000 tons of restaurant waste tipped into the Gulf of Mexico. The question you should be asking right now: if all of this worked and the data is unambiguous that it did, why aren't we scaling it everywhere? The barriers aren't scientific, they're institutional, they're economic. They're the inertia of regulatory systems built around hard engineering assumptions. The difficulty of getting coastal managers who spent careers specifying seawall dimensions to change how they think about the problem. The challenge of funding programs whose most impressive results take 5 to 10 years to fully appear in the data. And sometimes the simple human reluctance to trust a process that looks, at the beginning, like a barge full of restaurant garbage being dumped into the ocean. Mike Lenz trusted it eventually. Not because he was convinced by a report, because he stood at the rail of his boat and watched more fish than he'd seen in 25 years holding in the current around a shell mound. The data showed up where he could see it, in the water he'd worked his entire life. That's the conversation this program forces. About what we're willing to try. About what counts as a legitimate ecological intervention. About whether the definition of reckless ocean dumping can coexist with the reality of a 340% increase in fish biomass and $3 million in hurricane damage prevented from a $5 million program. Coastal engineers in Australia are asking that question right now. Researchers in Canada are running their own early trials. Cities with degraded urban harbors are looking at the Billion Oyster project and asking whether the same logic applies to their waterways. The answer increasingly is yes, and the timeline is faster than anyone thought. What comes next? The program has ended, the reefs have not. They are expanding right now in the Gulf of Mexico, building themselves from the inside out using nothing but biology and time. The shells deposited between 2007 and 2024 have become a self-sustaining ecological system, actively cleaning water, protecting shorelines, producing fish, sequestering carbon, and building structural complexity that will outlast everyone involved in designing the original program. 500,000 tons of oyster shells, discarded, written off, tipped into the Gulf without certainty that a single useful thing would result. And look what formed. Not just a reef, a feedback loop, a water treatment system, a hurricane barrier, a carbon sink, a fish nursery, an ecosystem that is, by every measurable indicator, getting healthier every year without any additional human input. The scientists who ran the monitoring surveys will tell you the data still surprises them. Not because they doubted the basic biology, because the speed, the scale, and the complexity of what assembled itself on that Gulf seafloor exceeded every projection by a margin that forced them to reassess everything they assumed about ecological recovery timelines. Nature, given the right conditions and the right materials, can move faster than we think. It can build more than we expect. It can fix, in years, damage we assumed would take generations to address. The Gulf of Mexico is proving that, and the coastlines watching Florida's experiment are paying attention. The question now is how many of them act on what they're seeing, because the shells are already there, piled up in landfills, scraped off plates, swept off processing floors, waiting to go back where they came from. The ocean is ready. The biology is ready. The only thing left to decide is whether we are.